We will wait for 2 minutes and then start. So hello everyone, this is Anjali Negi. I will introduce myself a little bit. So I am a PhD student pursuing my PhD in IIT Kanpur right now in the field of physical chemistry, theoretical and computational chemistry to be specified. So today again I have created some videos on gate problem set. So I'll share my screen now.
Hello everyone, in this video I will be solving GATE 2014 chemistry question number 3. This question states that the number of...
So the audio is also audible to you guys, right?
Yes, ma'am.
Okay.
of IR active vibrational normal modes of CO2 is. So let's move into some basic. So the normal modes of CO2 as according to our problem, but let's generalize. When we talk about vibrational modes or normal modes, so normal modes are actually the fundamental modes or vibrational modes of our non-linear, linear, or polyatomic molecules, which are the modes which are excluding after excluding the translational and rotational motion or vibrational modes. The rest are known as the normal modes. Okay. Also, we have to keep in mind that the normal mode is for any dynamical system or vibrational system is actually the pattern of motion in which all parts of system move sinusoidally with the same frequency with the fixed phase relation. So all part of the system is actually moving. So none of them is actually fixed. So you cannot say that in CO2 that the carbon will be fixed. It will also move. Okay. Now that is what a normal mode is, and that is how you can differentiate the normal with the local mode. Okay. Now coming that the non-linear molecule, for any non-linear molecule, the number of normal modes will be 3n minus 6. So I will explain it here that n is my number of atoms present in the molecule, and for a non-linear molecule, the 3 degree of motion can be assigned to translational degrees of freedom in x, y, and z direction, and 3 to rotational degree of freedom. So when my molecule is non-linear, um, the motion or the 3 degrees, 3 into n, that is a degree of freedom, is actually assigned with 3 as translational and other 3 as rotational in the XYZ direction. And the rest are called the normal modes, which is the displacement of the atoms from their mean position without the change of center of gravity. Okay, keep this in mind. The rest modes or vibrational modes are known as the normal mode, excluding the translational and rotational degree of freedom. So the rest will be normal mode, and these are the displacement of atom from their mean position without the change of center of gravity. And the example for these are asymmetric, symmetric, wagging, twisting, scissoring, and rocking. So the name, as you are reading here as an example, just search it because you can have a look at the GIF or particular videos doing the motion to get it understood. Okay, so for IR active, this is a note that for IR active, there has to be a change in the permanent dipole moment in the molecule for that particular normal mode. If you are asking about that the normal mode associated with CO2 is IR active or not, we have to keep in mind that whether the motion is considering giving us the change of permanent the dipole moment change or not. If it is giving us a change in the dipole moment, then it will be the IR active. Otherwise, it is IR non-active. Okay. Now, the number of vibrational mode for CO2. For CO2, as it is my linear molecule, my number of vibrational mode will become 3n minus 5. So these are the number of normal mode that I have associated with my CO2 as a linear molecule. So my n is the number of atoms present in the molecule, that is CO2, that is 3. Okay, so 3 into 3 minus 5, that will give me 4. So I have total 4 normal mode associated with my CO2 molecule, and those modes are, so the modes are, number 1, symmetric. So here you can see that this is in a symmetric normal mode, the direction of my motion or the vector of my oxygen on my oxygen are symmetric with each other, and in my asymmetric you can see that the vibration is actually asymmetric with each other, and so in the carbon atom. And similarly, in the bend motion, we will have two different type of bending happening in the CO2 as a linear molecule. You can see here. Okay. And so now, to find out the IR active modes among these four, we have to keep in mind that whether it changes the dipole moment or not. So the symmetric stretch, talking about the first one, it does not result in a change in the dipole moment. So initially for CO2 molecule, my dipole moment is actually equal to 0, correct? So that is there initially. But when it is doing the symmetric stretch after that, so again in the symmetric stretch, the dipole moment change will be 0 because it is symmetric stretch, and the dipole moment vector is again opposite to each other, pointing opposite to each other, the dipole moment vector I am talking about. So it will again give me the dipole moment equal to 0. Okay. So hence this mode is IR inactive. So I can write it as IR inactive. Now, the asymmetric stretch, this stretch does result in a change in the dipole moment, hence it is IR active. It is very clear, I think, because here you can see that the motion will have the bond expand and contract, and hence the dipole moment vector will have some value here, okay, and this will be IR active. Now the other two, that is the bend motion of the CO2 molecule, these two mode again will give me the change in the dipole moment, and hence these two are IR active. Okay, so the bend also result in the change in dipole moment, and hence these are also IR active. So overall I have a total of 1, 2 and 3 IR active modes. Okay. So the IR active mode, vibrational normal mode of CO2 is 3. The answer is 3 here. I will recommend you to go through the NPTEL reference lecture number 31 by Professor Manavendra Chandra, Department of Chemistry, IIT Kanpur. Here is the link I'm attaching. Thank you.
So if you guys have any doubt.
No, ma'am.
Okay. So after this particular problem that we solved, that came in GATE. So yeah, so this is another question which we can discuss here, that in the vibrational spectra of CO2, the number of fundamental vibrational modes, so when fundamental vibrational modes means normal modes, okay, common in both IR and Raman are. So yeah, so 3 of you are present here, so you can either unmute or type your answer in the chat box. So you guys are working on the problem?
0.
Okay, 0. Any other? Yeah, so Pranoy, so you are saying it is 0. So can you explain?
Ma'am, in the centrosymmetric molecules, which are active, that is Raman inactive, and vice versa.
Correct. So that was the one that Pranoy explained, that is called the mutual exclusion principle. So this principle is simply, it states that no normal mode, or the fundamental vibrational mode as we say, can both IR and Raman active in a molecule that possesses a center of symmetry or centrosymmetric molecule. Okay, so since yeah, so since my CO2 is a linear molecule, and you can see that it is very much symmetric in nature, and the center of symmetry is also present here, correct? So this particular molecule will not have any IR or Raman common normal modes. Okay, so is this clear with Hitesh and Gunasli?
Yes, ma'am.
So yes, so okay, is yeah, so after this so another video I will play.
Ma'am, your screen is not visible.
Yeah, I'm sharing it.
Hello everyone. In this video, I will be solving GATE 2015 Chemistry question number 45.
So audio is clear, right?
This question states that the potential energy versus reaction coordinate diagram for electron transfer reactions with rate constant K1, K2, K3 are given below, and we need to find out the increasing order of the rate constant. So we are given with 4 options with increasing order of rate constant K1, K2, K3. And so before moving into the conclusion, we should go through some basics. So the basic comes from Marcus' theory of electron transfer. So for electron transfer, let's assume, let's take one simple example like Ferrous and Spheric. Okay. And yeah, so here we have just for some time being, if you do not look at this part and just look at the conversion of Fe2 plus to Fe3 plus, and Fe3 plus getting reduced and becoming Fe2 plus. Okay, so this is the simplest example for electron transfer between these two iron complexes. So this is the product, and this reactants, and these are the products. So so if I include the steps, so this will be okay. So here we have one precursor complex formation where my Fe2 plus complex comes very close to my Fe3 plus complex, and this is what we call as precursor complex. And here, so this is in equilibrium with the reactants. So hence we have K1 as a forward rate constant and K minus 1 as a backward rate constant. And finally, when this get converted into Fe3 plus, which is getting oxidized, and this got reduced to Fe2 plus. Then we say this as the rate constant is followed by the rate constant KET, which is for electron transfer. Okay. Now finally this slash is indicated that here again these two complexes are in close contact, like in precursor complex. Finally they get separated, and we have our two complex as first one, my Fe2 plus got oxidized to Fe3 plus, and similarly my ferric got reduced to ferrous. Okay. Now, so I need to find the rate of this electron transfer. Okay. So I can write my precursor complex like this, Fe2 plus slash Fe3 plus, and this is the rate. So to set up this, I need to apply the steady state approximation here, and hence I can write the rate for this as K1, my concentration of my ferrous and concentration of my ferric, okay, complex. Yes, and then minus K minus 1 as my backward rate constant, the precursor complex, and my minus KET as my final after the electron transfer happened. Okay, and this equal to 0. Now, I will find out the concentration of this. So this is important for me. Okay, so here I am finding out the concentration of this. I will take it as separate here, and then the whole expression becomes something like this. Okay, here. Now, so in most cases, you have to keep this in mind that in most cases, the electron transfer rate is slower than K minus 1, that is KET, electron transfer, is very much, this rate constant is less than K minus 1. Okay. So if this is less than K minus 1, I can actually ignore this part in summation, and hence my equation, my expression will be this. Okay. Here, do not get confused because I have just written the concentration of Fe2 plus, and here concentration of Fe3, and okay, just I made it a little short here. Okay, so these are concentration. Now overall rate of the reaction R can be written as the rate constant KET. This is the concentration of Fe2 slash Fe3. This is my precursor complex that was formed before the electron transfer took place. Okay. So my R, that is my rate of the overall rate, I will substitute the value from here, okay, to in this new expression of my overall rate, and thus I will get my R is equal to KET, and K1. You can write. I can write this particular expression as K observed, okay, and this will be K1, and also I can write this one as K1, capital K, okay, and this as KET. So my K1 is actually a pre-equilibrium constant because it is equal to K small k1 upon small k minus 1, okay. Now my KET is important for us here because this is the rate actually related to the electron transfer, okay. And yes, so the question here is that why aren't these reactions instantaneous? And also, so first question is that we get into mind that why we have equilibrium getting established there, and then finally there is a KET, which is obviously defining the rate of electron transfer for the reaction or between the complex to take place. So this is definitely not instantaneous. And again, the next question that we should asks us that what is the difference between the ferric and the ferrous ion. So when I'm talking about ferric and ferrous, so Fe2 plus this complex has with OH2, H2O. So this has a distance of between the metal and the ligand is 2.1 angstrom, and the bond distance get more short when it is Fe3. So this becomes 2 angstrom. Okay. Now there is a problem in which energy is questioned. So when we transfer an electron, so the electron will get transferred between this ferrous and this ferric complex, where my ferrous will get converted into ferric and my ferric will get converted into ferrous. Okay. Now what will happen actually in the complex structure, that the bond length will get here, it will get compressed, or it will get reduced, the bond length, and here it will get expanded, or the bond length of my ferric will get because it is converting to ferrous, therefore the bond length will get increased. So the problem is that we have to consider the difference in the energies also, and question that what will be the when the electron transfer is taking place, what will happen with the energy. So let's draw. For that, we have to draw the potential energy surface for a precursor and our supermolecule, or supermolecule. So you can call the precursor complex as a supermolecule also. Okay. So if I am writing my precursor complex as a reactant, also after that electron transfer took place, I can write it as a product. So here you can see that this is a ferrous complex. Okay, so I'm just here denoting for our understanding one bond with OH2. So here this complex is actually, this is whole 6. Okay, but just for our consideration, I am only demonstrating a bond length, and you can I also made it a little observable that this bond length is a little bigger than this one, and this one is smaller bond length than this one. Okay, so that I tried to do to get to observe about the actual difference in the structure. Then this is what happening here, that the reactant, like here in this precursor complex, will be getting converted into something like this. So this I am taking as a reactant, and this I am taking as a product. Now I have to draw the potential energy surface for these. Like this is my reactant and for my product. So now here the electron is moving within the molecule, so itself, and that's basically some electronic transition. So consider here that these two complexes are very close to each other, the ferrous and the ferric complex, and now the electron transfer will take place between them. So this as a whole is I am calling it as my precursor complex, and this is I am taking as a whole, as a one unit. So I am saying that the electron transfer is taking place within the molecule here is my precursor complex. Okay, now when I am saying about the electronic transfer taking place within a molecule or my precursor complex, what I will get into my mind that that the electron transfer is related to the electronic transition that we studied that take place in a molecule and or atom. So that will be drawn here as a potential energy surface. Now here, so this y-axis is denoted for the energy, okay, unit, and for this x is your reaction coordinate. So for your reaction coordinate, keep in mind that now for reactant and product both are as my precursor complex, or and my again when the electron transfer took place, it is again not separated yet, so it's a complex again. Okay, so this particular parabolic curve is denoted to my reactant. Okay, here you can write it as FeA, FeB, where my FeA has a 2 plus charge, and my FeB has a 3 plus charge. Okay, and after it got converted to the product, here you can see that my Fea get oxidized and my Feb get reduced. So this particular curve, parabolic, another parabolic curve, is denoted to the product side. Okay. So again, the x-axis is actually the asymmetric stretch, because it's the asymmetric stretch. Why? Because you can see that the bond length as it is changing in for my reactant and my product precursor complexes. So you need to take that this is not a symmetric stretch but a asymmetric stretch. Okay, and we can also say that this Fea, Feb, the reaction coordinate is actually the nuclear coordinates. Okay. Now, what is the time scale involved to move along the coordinate? Now, to move along the coordinate, what will be the time scale? Okay, and I can write that as a mu EL, or electronic, that is my frequency of electronic motion, which will be around 10 to the power 16. So per second. Okay, and my mu vibrational will be frequency of vibration of my metallic bond, that is my metal and ligand bond. The frequency of that bond vibration will be around 10 to the power 13 per second. Okay, this is some example for any particular, like for this iron, ferrous and ferric. This is 300 centimeter inverse. Okay, it will be varying depending upon the complexes or the molecules. So mu vibration Cc will be, like, for example, 1000 centimeter inverse will be around 10 to the power 14 per second, and mu, like solvation, you have for solvent, you have to also take into account the rotation of it. Okay, so the rotational frequency will be around 10 to the power 11 per second. So we have a large time scale from varying from electronic transition frequency 10 to the power 16 to 10 to the power 11. That is a rotational frequency for my solvent molecule per second. Okay, so we cannot actually couple these modes. Okay, so the electron is going to move much faster than the nuclei, hence I cannot couple it with some other modes. Okay, so because there is a very large difference, so coupling is not taking place here. Now the ways of electron transfer that I have to keep in mind between my reactant and my product precursor complexes is this. So just considering again the electronic transition. So here are the two parabolic curves denoted to one reactants and one to the product. Okay, now so electron transfer can take place in two different ways. Either optical transfer is taking place electronically, or either the thermal transition taking place. Okay, so in thermal reaction, what happens is that the input energy is only via collision of nuclei. Again, so the energy in thermal reaction is only via the collision of nuclei. So there is no way in the time scale of electron to jump and go there. I mean, from here to here, it cannot, the electron cannot get transferred in a thermal reaction just by collision, because the time scale of the collision and the electron transfer is way more separated and different. So we need to move along the ground state surface with the collisions up to where it is possible for electron to be in reactant or product. That is, the electron can jump and get relaxed to the product side. So what they are saying, what is happening in the thermal reaction, that here my electron, my product here, this is denoted to reactant. So my reactant having some collision, it will be possible for them to thermally get excited, and the energy will rise up to here where there is a point. So how the electron transfer takes place, that this will be the point where my electron can be in either reactant curve or either product curve. Okay, so here it can jump so and get relaxed to the product side, and finally we get a product. Okay, So therefore, the barrier to the thermal reaction, I can write it as delta G star. So yes. So you can write here it as delta G star, that is the thermal barrier for the electron transfer. Okay. Now using, if I am using photon or optical transition, the using photon, you can directly go vertically up such that the optically EOP transition is seen. So the vertical transition is something which is for the fixed nuclear position and happens instantaneously. Okay. And the horizontal transition that we have seen in the thermal condition or thermal reaction, we are moving at a time scale of nuclear motion. Is that correct? Because you are moving in the reaction coordinate in a thermal transition to take place horizontally, and so that you get from your reactant you get the products. Okay. Again, this is something which is not necessary for our problem, but you can just discuss that the ER for reactant, optically you can write it as lambda x square. This is x, okay, and EP for product, alpha. Lambda x minus 1 square, and again you can write the delta G star, that is the thermal barrier for the electron transfer, is 1 by 4 of lambda. Okay. So rate of electron transfer, that is the KET, is what we need to find out. That is using the transition state theory. We find out using the transition state theory if we apply. So these are actually some extras you can go through, but I will just quickly complete it. That the equilibrium constant in transition state theory, you write it as K is equal to C dragger upon C, where C dragger is the concentration of the transition state and my C is the concentration of my reactant. So this is your reactant side and this is your product side of the potential energy surface. Then mu n is your nuclear frequency at transition state. They destroy the transition state. So this frequency, the nuclear frequency, is actually destroying my transition state and making it get converted into the product or either the reactant again. Therefore, the total rate will be written as mu n upon into C dragger, and I can write it as K is equal to mu n K C. Okay, and the KET here can be written as mu n, that is the nuclear frequency, into K. And my K here is again you need to keep this in mind. This is the capital K, which is the equilibrium constant. Okay, then I can again write it as E to the power exponential to the power minus delta G dragger upon RT, or this is dragger is used for the transition state theory, and in transition state theory is a biomolecular reaction. We study it like that. But in electronic transition or in Marcus theory, we are considering example of unimolecular reaction, correct? So you can write that not as dragger but as minus delta G star. Okay. And again, you can substitute your delta G value, that is lambda by 4. And this will be the transition theory for bimolecular reaction, as I have told you. And here we apply it for the unimolecular reaction for my electron transfer. Now, finally, this is my KET, that is my rate. So this is mu n e to the power minus lambda upon 4 RT. Okay, and so there are much more detail after this because we have to substitute this mu into much more simpler idea, simpler something that we can express KET as. Yeah. So I will jump to the last slide of my solution. So the potential energy of this that we were talking about. So this is the electron transfer reaction, okay, and so here we have potential energy, okay. So this is basically the example of thermal electronic transition or thermal electron transfer reaction. So you remember that the barrier to the thermal electronic transition was this delta G. star, correct? So this is your reactant curve, and this is your product curve, and this is your reaction coordinate in x-axis, and here in y-axis you have energy, that is the potential energy here. So see, this is your, say it is 1, okay, because we know this is delta G dagger, and this will be the barrier for my electron transfer. And again, so the barrier actually that I have talked to you about, if you will go something like this, that this will be my delta G dagger, but actually this is not. So wait. Yes, so this is the ground state, correct? And this is again ground state of, this is for reactant and this is for product. Now this is my ground state and this is my ground state of my product curve. So that thermally what was happening, that the reactant do collisions and increase their energy up to the point where my electron get transferred, correct, between can jump between either the reactant curve, potential energy curve, or either the product, okay. So here it has to travel like this, increase its energy from the ground state from using collision, and here, and then get relaxed to the product side. But what is happening in this particular curve, that in the particular ground state of my reactant only, it can actually jump to the product, and hence there is no further delta G needed for, or collision extra energy needed for my reactant to get excited and increase its energy. It can actually do the electron transfer here only, because the two curves are intersecting there where the ground state of my reactant is present. Again here, so these you can actually, yeah. So from here, my electron will get, my reactant will get excited, and my electron can jump at this intersection of the two potential energy curve and get relaxed to the product side. So this will be my delta G star, and this will be my delta G star. But for here, as you have seen, that there is no need for delta G star, or a minimal energy is needed only, because it is actually intersecting at the ground state of the reactant state only, okay. So my, obviously the rate is much faster in K2. So K2 is the fastest rate. So okay, and then we have K1. So we have K2, we have then K1 as the next faster rate, and then K3. Yeah, so the D option fits well for this. And I will particularly ask you to go through the reference. This is from Caltech University. So this is Electrochemistry Lecture 18, Marcus Theory Caltech. Okay, and I'm attaching the link below. Thank you.
So if you have any doubts, you can ask or type in the chat box.
I have one doubt, ma'am.
Yeah, Pranay.
You tell that Fe2 plus OH and Fe3 plus in precursor molecule,
Yes.
Fe3 plus OH having asymmetrical stretching. Why do so?
Yeah, here, so I was So we were drawing the potential energy surface for the this precursor molecule. So here it was acting as a reactant where that electron transfer was taking place from Fe2 to Fe3, correct? And it was an asymmetrical stretch because if you look at the curve, okay, yeah, so this is the two curve. Okay, then the first curve, if you see that from here where my Fe2 and Fe3 are A and B and are present here in the ground state. So just this is the X is my nuclear coordinate. Okay, or yes. So then if you assume the distance, actually this will be the distance between Fe2, Fe3 or Fe2 and the ligand, because I said the asymmetrical stretch because the bond length will get will be different when it get converted to the product. So the bond length was actually expanding or elongating or contracting when it was getting converted to the different ionic state of the iron itself. So the asymmetrical stretch is necessary for, even if you see the transition state theory, so there also when you are at the transition state, so there is a frequency which is responsible for the transition state to destroy the transition state and make get it converted to the product side or to the reactant side. So that is also there also we say that there is also a asymmetrical stretch is happening. So I think it will be much more clear, but from how I can explain is that, so there also if we were following the so I think have you gone through that the contour diagram of reaction coordinate of transition state theory?
Yes, ma'am.
Okay, so wait, I can just share one of my screen and then so if I remember the transition state theory also, so if say your it was like A B C, so if you just consider that this is something like your transition state, and before this it was AB plus C, and after this it is A plus BC, and so something like that your reaction, if you go through the reaction coordinate, which was I think here it was for my reactant, and so it was AB and plus C here, and when it reaches here it was A plus BC, and the contour that was created here were something like here the transition, I think I have one video of it, so I will just try to explain it here, that this was the transition state, okay, which was present here. So when we were actually explaining the direction of our reaction, we were using the tangent. So the tangent to the contour was something like this, And to explain whether this direction is asymmetrical or symmetrical, what you will do, that you will just take it like this, like for example, this is wrong actually, yeah. So to explain the stretch, whether you are moving into what direction, so see, at this point of your curve, so see, at this point of your curve, your AB distance is what is a little bigger or larger than the one here, okay. So this particular stretch was contracting, and then so does any one of you remember this? Because I am also forgetting a little bit. So this was something which was denoted the asymmetrical stretch. I think I have the notes somewhere. Okay, I have those slides. So this was the question that I explained in some of my videos. So this was for the pre-exponential factor that we have to calculate. So I explained it using the Eyring equation and theory. So yeah, in this particular slide, if you will see that so this is the reaction coordinate, particularly this one x is denoting for RBC, and this one is denoting for RAB. And so along the transition state, it's neither x nor the y vibration, but rather if I move along the red one, it is symmetrical vibration, because ABX is equal to AB is equal to BC, that is the x equal to y. Oh yeah, okay. So see, along this direction, correct? So this direction, your y and your x value, it's a linearly increasing, monotonically increasing direction of this arrow, correct? So this one will be symmetric with respect to AB and BC both. So the symmetric or asymmetric stretch that we were talking about, either in this transition state theory or the one that we discussed just a few minutes ago, we were always talking about the one for the precursor complex or the transition state. So this is the transition state. You can also assume it as a precursor complex, like there will be ligand in between or so, okay. So I denoted the precursor complex like this, correct? So this is the complex, this is the other complex, come very close to each other, and such that the symmetric or asymmetric stretch that we were talking about were with respect to this particular complex which is forming just before the electron transfer, right? So the stretch that we were talking about is the bond length or the distance between the metal and ligand, because obviously when my Fe2 will get convert or will lose one electron, get convert into Fe3, the bond length of my metal and ligand will get contract, as we have seen. So for this contraction, if there in the other half also, if there is a contraction similarly, not the elongation, then it will be called as the symmetric stretch. But what was happening, that at one half of the precursor complex we were observing the contraction of the bond length, but on the other half we were observing the elongation, and this is what we call as the anti-symmetric stretch. And why so? Because in this direction, if you will see that the distance AB or BC bond length is actually always equal, correct? X equal to Y mathematically, or AB equal to BC vibration. But when we move for the in the transition state theory also, along the transition state to the formation of the product, what happened that the orthogonal to the previous one is known as the asymmetrical stretch, because if you see here the curve, so the bond distance is actually contracting to get converted to the bond product. Okay, if you symmetrically vibration, nothing happen, but if you do the asymmetrical vibration, so BC bond will compress and AB bond will elongate, and then only you will get the product, because one bond has to break and other bond has to form in the transition state theory. Similarly, in the precursor complex, the metal and ligand bond is not breaking, but it has to change the bond length. So that is why it is asymmetrical stretch. So am I be able to make it clear? So Pranoy?
Absolutely, ma'am. Absolutely, ma'am.
Okay. So
Thank you.
yeah, welcome. Yes, so I will share another tab. That's the last video, or I can actually stop also, because it's a 8-minute video. So you guys want to continue? If you have any other session, then we can stop, or we can continue also.
Yes, ma'am.
Okay, so I'm continuing. Last time someone was requesting me to stop because it was exceeded the time and they wanted to attend some other session. So if you guys are okay with it, then I will continue.
Ma'am, there is another NPTEL section
Hello,
is there.
everyone.
Yeah, that's why I was asking, because I don't have a problem to continue, but if you have the session you want to attend, then I can stop.
Ma'am, another section is there, so that
Yeah, that's what I'm saying, that it's fine, we can continue in the another session that we have. So we have 2 sessions left, so another 2 last sessions, so we will continue there also. So it's time. So if you guys have any feedback and anything you want to add, then I can convey your feedback.
Yeah, ma'am, you can put more new questions into this slides, so that it's like 2022 questions or 2021 questions.
Okay.
Great.
Yeah. So Pranay, actually 2020 and 2022 questions are already covered from because we started from the starting years, like a new 2022 and then 2021, then 2020, and then we are moving to the previous years. So when this gate session started, I think I have also solved the 2020 paper questions set, and I think you missed. You can go and watch the live videos of others also. Also in the gate portal itself, if you will go and watch the video solutions, so there is a section you can choose the chemistry and then go for the video solutions, and there you can choose the year. So I think 2020 or 2022 is uploaded or is in process, because videos are already prepared from each instructor that we were assigned. So I have also created the videos and submitted there, so it is there. Either they will upload because I am doing the 2014 or 20 next I will do 2013 and 12. So that's the way we were processing, so it is already completed. So either you will be able to find it on the gate portal itself. Okay.
Okay, ma'am. Thank you.
Yeah. Okay, thank you.